Welcome to the next part of our lecture on reaction mechanisms, a very important topic in organic chemistry. Now, in the introductory part, I did talk about the types of fusion reactions. I did mention homolytic fusion and heterolytic fusion. And I said homolytic fusion leads to the production of free radicals, and heterolytic fusion leads to the production of nucleophiles and electrophiles. Now, I mentioned something like the inductive effect and all that, but I will try to, that was just like a summary of the introduction. So I will try to, expatiate on some certain things today. So let's talk about organic chemistry. And what we're talking about is reagents, types of reaction, or let's say reactions, and reaction mechanisms. Okay, so for the reagents, all right. Now, during a chemical reaction, there is a species that undergoes an attack, and then there is an attacking species. What undergoes the attack is called the substrate, and what the attacking agent is called the reagent. Okay, so for example, we saw the three types of reagents here last time. So reagents are actually substances which are being added to organic molecules to cause them react. Okay, so that's the definition of reagents. Substances which are being added to organic molecules to cause them to react. Those are reagents. And the reagent is the attacking species during a chemical reaction, and then the substrate is the species which is being attacked during that chemical reaction. All right. So we saw nucleophiles, electrophiles, and free radicals. And so we can say that reagents are classified according to their reaction sites. Okay, they are classified according to what we call reaction sites. Reaction sites. Now, what is a reaction site? A reaction site is a region of high or low electron density. Now, a species, for example, you saw the nucleophile, that is an electron-rich species. That we call it a nucleophile because it has a site of high electron density. And then it went to the electrophile, the electrophile, and we said that it is an electron deficient species. Why? Because it has a region of low electron density around it. Okay, and examples of nucleophiles. Okay, examples of nucleophiles are, you have double bonds. Okay, maybe carbon to carbon double bonds, carbon to oxygen, all right, and so on. Those are electron-rich sites. Then we have, we also have negatively charged species like OH minus. Okay, lone pairs of electrons are nucleophiles. Lone pairs of electrons are nucleophiles, double bonds are nucleophiles, and then we have also negatively charged species are also nucleophiles. Then for electrophiles, examples of electrophiles are positively charged species, electrophiles. Electrophiles are positively charged species. For example, we have CH3 plus. Okay, we have bromine plus, okay, Cl plus, and so on. We saw that nucleophiles and electrophiles are being generated via heterolytic fusion, because during heterolytic fusion, the two species which are connected by a covalent bond are of different electronegativities. So one is going to pick up all the electrons which is found in the bond, and the other ones are going to pick up, will go with no electron. The one that goes with no electron is electron deficient, so we call it the electrophile, and the one that goes with all the electrons is called the nucleophile, okay, because it is electron rich. Then we saw another type of fusion reaction which leads to the production of what we call free radicals, which is homolytic fission. Now it occurs in like diatomic molecules like chlorine, chlorine is joined to chlorine. So when there is homolytic fission, you're going to have two chlorine radicals produced because both of them have the same electronegativity. If you didn't get it too clear here, because I'm not writing too much, it's a revision. You go back to the first lecture, you get it clear before you come back to this part. Now, what are some of the factors that are going to be affecting the rate of a chemical reaction? So these are some of the details which I did not give in the introduction. So what are some of the factors which are going to affect the rate of a chemical or an organic reaction? We are going to have what we call inductive effect. I explained inductive effect in the last video, and I said is the ability of a group which is attached to a carbon atom to either donate electrons, okay, or to withdraw electrons from the carbon atom. I quoted an example. I say if you take carbon, for example, and bromine is more electronegative than carbon, all right, in a compound, and so bromine would rather be pulling electrons away from this carbon atom, and so we call it negative I effect. And for positive I effect, we saw that bromine, okay, if you, for example, you take something like sodium attached to carbon is more electronegative than sodium, and so sodium would rather be donating electrons to the carbon atom, so we call it a plus I effect. Okay, we call it a plus I effect. Why? Because the group here is donating electrons, but this one is rather withdrawing the electrons away. Okay, so this one you're calling a plus I effect. Okay, the ability of a group which is attached to a carbon atom to either donate electrons or withdraw. And we have seen the two types, plus I and minus I effect. And then another one that we are going to discuss is going to be, which we are going to discuss details in this lecture, is going to be what we call the mesomeric effect. Okay. Now the mesomeric effect is the complete transfer or a complete shift of an electron pair from a substituent group. Okay, an electron pair from a substituent group, which occurs if that substituent group has a lone pair of electrons or a double bond. For example, we usually see this mesomeric effect in carboxylic acid. Okay. Now in this oxygen is more electronegative than hydrogen. Okay, so it pulls electrons from hydrogen. Okay, making, of course, hydrogen is partially positive and this one is partially negative. But this oxygen has lone pairs of electrons. Okay, so what happens is that these lone pairs of electrons here can be shifted, all right, towards this carbon atom here. Okay, towards this bond. Okay, and then these lone pairs of electrons which are here. All right, remember this is a double bond. I said it's the complete shift of an electron pair. Okay, of electrons or of electron pair, which occurs when the substituent group can have either a lone pair or a double bond. So here, or a multiple bond, not just a double bond, because you can also have a triple bond. Okay, so here we have this double bond. You can also have a shift of these electrons from here to here. So we call that action the mesomeric effect. Okay, we call it the mesomeric effect. That complete shift of electron pairs when a substituent group has either a lone pair of electrons or a multiple bond. Now, of course, you see when the electron pairs are being shifted towards one part, it makes the species to become more reactive. Okay, and then we also have what we call the steric hindrance. Okay, we have what we call steric hindrance. And please, before that, let me just give you an example of another example of mesomeric effect. So this is the benzene ring, and we have our OH. Okay, we have our OH like that. So there's a lone pair of electrons on this oxygen here. You can be able to donate. There can be that shift of the lone pair of electrons towards the benzene ring. So that is another example of mesomeric effect, and that is why when the OH is attached to the benzene ring becomes very, very more reactive. Okay, due to that increase in electron density. So that is it. So we have the last one, all right, which is going to be what we call the steric hindrance. Steric hindrance, or the steric factor. Let's call it the steric factor. Okay. Now, for the steric factor, it depends on the spatial arrangement of atoms or groups. Okay, in a molecule. For example, now that spatial arrangement of group of atoms around a carbon atom or in a molecule can influence the reaction either positively or negatively, so you can make it either to be slow or not. And it's a perfect example that I'm going to use. I'm going to use two examples. A esterification reaction. Now, a esterification reaction occurs very simple with it occurs between carboxylic acids. For example, if I take ethanoic acid, which is CH3 COOH, okay, plus CH3 CH2 so that's propan 1 ol. If I add this reaction to, if I add propan 1 ol, okay, to ethanoic acid, of course I'm going to obtain propyl ethanate. Okay, I'm going to obtain propyl ethanate. Now, if I rather add this same ethanoic acid, okay, if I add the same ethanoic acid to say CH3 CH2 or CH3, okay, this is propan 2 ol. So you see, this is propan 1 ol, and this is propan 2 ol. Okay, this is propan 2 ol. Now with propan 1 ol, okay, if with propan 1 ol, the reaction rate here is very high than this one. So the reaction rate of esterification of propan 2 ol, okay, is half that of propan 1 ol. It means that propan 1, the reaction rate here when you are esterifying propan 1 ol is about 2 times faster than when you are esterifying propan 2 ol. Why is this so? Because surrounding this carbon atom here, we have 2 CH3 groups, okay, which are going to hinder the incoming group which are supposed to react, okay, the incoming group which is supposed to react here with this group, okay, on the carbon atom here, okay, it is going to hinder it, so making the rate of reaction to become slow. Another place where we see steric hindrance again, okay, is in the reaction of carbonyl compounds. Now, they usually say that aldehydes are more reactive than ketones. So this can be an aldehyde, a ketone is a group like this. It's having 2 massive groups on both sides of it. Okay, and an aldehyde is having something like this, just H. Okay. Now, if you are adding 2 molecules, if you look at it on both sides of this carbon atom, you have 2 massive groups which are found on both sides of it. So it is going to hinder the group which is going, so it blocks this group which is supposed to react with the incoming reagents. So these 2 groups here are massive, so we call it steric hindrance. And with this one also, the same thing is going to happen. All right. With this one, the group here is exposed. It's not really hindered that way because it has just one group on one side, one massive group on one side of the carbon atom here. Okay. So this is that steric hindrance is the reason why aldehydes are more reactive than ketones. Okay, and the same thing why propan 1 ol can be easily esterified than propan 2 ol. And in the case of this one also, okay, we also have the case of the notion of steric hindrance. So there are 2 reasons why aldehydes are more reactive than ketones. The first one is the inductive effect. If you look at it, these 2 groups here, okay, are donating electrons. So when they donate electrons to this carbon atom, it makes this carbon atom here to be kind of negatively charged. Okay, since they receive nucleophiles, of course, which are also electron-rich species, this species here will be less positive, and so you make it to be less reactive. That's the first reason. Okay, but with this one, it does not receive too much electrons, okay, from this arrow group here. So it still has a partial positive center around it and can easily react with the incoming nucleophiles. Alright, then the next reason why aldehydes are more reactive than ketones is due to steric hindrance. So we have steric hindrance in the ketone, but we don't really have steric hindrance in their aldehyde. Okay, so we have looked at the 3 factors which can affect a chemical or an organic reaction. We have talked about the inductive effect, the mesomeric effect, and the steric factor. Okay, and we have seen the examples where we can be able to apply the steric factor for explanation. Alright, so the very first thing, in the first video I explained the different kinds of reactions to you. I said we had addition reactions, we have substitution reactions, and we have nucleophilic reactions. Okay, I tried to elaborate the kind of mechanisms to you, so we'll just go straight to the point without wasting much time. You can go back there and get the different types of reactions, although in course of the lecture we are going to get all of the updates. Now, Here we have, if we start with a substitution reaction, because we are supposed to look at the substitution reaction, and we have to get the mechanism, substitution reaction. Now with a substitution reaction, we have, like in an organic molecule, so we have a substitution reaction is a reaction in which one atom or group of atoms replaces another atom or group of atoms in an organic molecule. That's why we call it substitution. Meaning that you're keeping, maybe you're picking an orange and you're keeping pear. So you are substituting the orange, okay, with the pear. So that is what is happening for substitution reaction. Now here we are going to see electrophilic substitution. We will see free radical substitution, and we are going to see nucleophilic substitution. But we are going to start, I always like to start with free radical substitution first. Okay? An example of the free radical substitution, so we'll just look at it and then we'll go to the mechanisms at once. So an example of a free radical substitution, For free radical substitution reaction, we have an example is the chlorination of methane, okay, in UV light. I'm sure we have had this in many past GC questions. So we have plus chlorine in UV light to give us CH3 chloromethane plus HCl. Okay, chloromethane plus HCl. Okay, so what happens is that we are going to have, you see, one of the hydrogen atoms has been replaced by a chlorine atom. Okay, so we are going to see how does this take place, what is the reaction mechanism. Now for the mechanism, the reaction mechanism explains the detailed steps. Alright, it's simply the detailed and sequence of steps which occur in process of converting a molecule, an organic molecule to a reactant to a product. Okay, that's what we call a reaction mechanism, the detailed steps, telling you how the molecules combine, alright, where are electrons added or where are electrons being subtracted. So here we are going to have in the very first step we call it the initiation. Okay, for the mechanism of free radical substitution, we have the initiation reaction, we have the propagation, that's the second stage, and we finally have the termination. Okay, we have the initiation, we have the propagation, and we finally have the termination. Now for the initiation step, okay, we are going to have just one equation. And what happens during initiation, we are going to have this chlorine molecule being acted upon by the UV light. Okay, the UV light acts upon the chlorine molecule to produce two chlorine radicals. So I'm going to have a chlorine radical plus another chlorine radical. Okay, that's the first step that occurs in initiation. Now during propagation, the radicals are being consumed and radicals are being produced. So these radicals now are very high reactive species. And remember, free radicals are produced by homolytic fission, and a radical is a species with an unpaired electron. So each of these chlorine radicals has an unpaired electron, and they are highly reactive species. So this chlorine radical will react with the CH3 molecule, with the CH4 molecule, that is a methane molecule, to produce a CH3 radical plus HCl. Okay, plus HCl. Now, we say that radicals are being consumed and radicals are being produced. This CH3 radical, okay, will react with other chlorine atoms which are present within the molecule to now produce CH3Cl plus another chlorine radical. So you see, this radical will help will react with this chlorine molecule in order to give us CH3Cl plus a chlorine radical, okay, which can now undergo further attacks. Then for the termination step, we are going to have a chlorine radical. We can have a chlorine radical combining with other chlorine radicals, okay, to give us Cl. Okay, please. I don't think we have. Okay, please take note of the first step here, mechanism initiation. We have splitting of the chlorine, homolytic fission of the chlorine by UV light to produce 2 chlorine radicals, and then propagation here we have radicals have been consumed, so the chlorine radical reacts with CH4 radical to produce CH3 radical. So with CH4 to produce CH3 radical and HCl, and then the CH3 radical react with other chlorine molecules present within the medium to produce CH3Cl plus a CH3 radical. Now for the termination step, we have 3 reactions. Okay, so if I can be able to wipe this part for now. So for the termination step, for termination, we are going to have CH3 radical. So we can have, let's say, chlorine radical reacting with another chlorine radical, okay, to give us Cl2. Then, of course, termination, the reaction is coming to an end. We have CH3 radical reacting with other CH3 radicals, okay, to give us CH3, okay, and then we have CH3 radicals plus Cl radical, okay. You just see radicals are simply just combining in this stage in order to give us molecules, okay. In this stage, radicals are combining to give us molecules. So CH3 radical combines with Cl radical to give us CH3Cl, okay, CH3Cl, and that is it for the reaction mechanism, okay, for free radical substitution reaction. So if you are being asked, as it's always being asked in the exam, you make sure that you give it. You should know the different steps. We are given the initiation, we just write the propagation, and finally this is the termination step of the reaction. And that we call it, we can say that is the end of free radical substitution mechanism. Okay? And now we are going to go to electrophilic substitution. Alright, we'll move on to electrophilic substitution mechanism. Where does electrophilic substitution mechanism? Now, if you are asked to describe or to define free radical substitution reaction, what are you going to say? You say it is a reaction in which free radicals substitute, replaces a free radical replaces an atom or group of atoms in an organic molecule. Okay. And for an electrophilic substitution, you will say that it is a reaction in which an electrophile replaces an atom or group of atoms in an organic molecule. And if it's a nucleophile, the same thing you are going to say, that it's a reaction in which a nucleophile, if they ask you to define nucleophilic substitution, you say it's a reaction in which a nucleophile replaces an atom or group of atoms in a molecule. Now let's look at electrophilic substitution. Now, electrophilic substitution occurs on the benzene ring. Okay, substitution occurs on the benzene ring. Okay, now this is one of the reasons most of the time when they ask you why is it that benzene does not contain double bonds, you say benzene does not readily undergo electrophilic addition. Now, I will just try to say some things about benzene. Normally, the first structure of benzene that was discovered was called a calculate structure, which can be something like this. We can call it the calculate structure of benzene, or it could be something like that. Okay, that is the calculate structure of benzene. But in a real sense, if you name the compound, it's going to give you We're going to have cyclohex 1,3,5-triene. Okay, you're going to have cyclohex 1,3,5-triene. That is the name of that compound. Now, normally the real structure of benzene is actually this. Alright, this is actually the real structure of benzene. Why do we write this? What does this circle represent? It represents a system of delocalized pi electrons, because benzene is very, very stable. And how do you know that? If they ask you to give reasons why this is not the structure of benzene, June 2015. So what you do is that you're going to say benzene, number one, benzene does not readily undergo electrophilic addition reactions. Because if it has double bonds, it is going to be going on electrophilic addition reaction easily. But instead, benzene does not readily undergo electrophilic addition, telling you its stability means that it does not contain double bonds. It rather contains a system of delocalized pi electrons. But Okay, that's it. That's the first proof. The next thing is that the bond length. Okay, the bond length in the benzene molecule, because a double bond is shorter than a single bond. Okay, a double bond is more stronger than a single bond, and of course a double bond is more shorter than a single bond. Now, since it means that if you are measuring the bond length, all right, in all of these molecules here, the bond length here is going to give you, you have different values. Okay, you are going to have different values of the bond length. But in benzene, okay, in benzene, all the bond lengths are the same. All right, all the bond lengths are the same in benzene. So I'm going to end here for this part of the lecture. We'll continue in the next part of the video. In the next part of the video for the reaction mechanisms on the electrophilic substitution, where we are going to explain it proper. Okay, so make sure you follow our lectures and you subscribe to the YouTube channel. Right? Thank you very much, and see you in the next video.